This is the second part of our lectures on Earth and the sky. So let's move on with lecture 2b, the motion of the Earth and the Sun. And here's a little graphic that just represents the ancient Egyptian view of the sun moving across the sky. Here is Horus with the sun or the eye of Ra on his head moving across the sky. And this kind of represented in ancient Egyptian belief systems the sun and its journey across the sky. So, we've already talked about one coordinate system, that being the altitude and azimuth system. Here we're going to make a few more definitions, and with those definitions give ourselves a second coordinate system that has a few advantages over the Altaz system we discussed in the previous lecture. We'll discuss the solstices and what they mean for the Earth, and equatorial coordinates, as I just said. We'll then talk about the seasons, how they relate to things like the solstices and the ecliptic, and we'll look at the seasonal effects. So, let's talk about the ecliptic. What do we mean when we talk about the ecliptic? Well, we've already defined one large circle around the Earth, that being the equator. But this was an imaginary construct, a circle we placed essentially around the waist of the Earth's sphere. When we talk about the ecliptic, what we're talking about is the path that the sun makes in the sky over the year. Now, what we mean is, if you go outside over the period of one day, you can see the sunrise and the sunset. But over the year, the sun reaches different maximum elevations. It actually changes its position in the sky as the year goes on. Its maximum elevation changes. So the sun appears to shift in position at the same time of day each day over the period of a year. The path that the sun traces out in the sky over a year is referred to as the ecliptic. Now remember, the Earth is the thing that is moving. The sun, relative to the Earth at least, is standing still. So it isn't that the sun is actually moving across the sky during the day, it's us rotating. It isn't that it's the sun moving around in the sky over the course of the year, that's us rotating around the sun in our yearly cycle, in our orbit. So, the ecliptic, the path the sun traces out in the sky over the year, is actually the plane of the Earth's orbit that we're seeing. Now, something some people do notice and others don't is that the stars and the sun in the sky move a specific direction. The sun will rise in the east and set in the west. And this is due to the direction of the Earth's rotation. So from this we can tell which way the Earth is rotating. So we've just said that we can trace the path of the sun in the sky over the period of a year. And we've already, in our previous lecture, defined what the celestial equator was, this ring around the center of the Earth. Here's our north and south celestial poles we previously discussed. So the ecliptic, if we plot it out as a circle, will look like this. And as you can see, the Earth, as it rotates around the sun, the ecliptic is not perfectly coincident with the equator. This means that there's a 23.5 degree tilt to the Earth. The Earth is not spinning in the same plane as the sun. It's slightly off center, and so it's spinning at an odd angle of 23.5 degrees. And we refer to that as the obliquity of the ecliptic. You don't really need this term, but that's what this is referring to. The obliquity is how far off the Earth's rotational axis we are in terms of our orbit. So here's the ecliptic, here's the equator. And this is going to have various effects. So why does the sun change position in the sky? Now I realize that when you go out and look at the sun the sun is shining, so you can't actually see the constellations. But we can define the position of the sun towards a specific constellation. Just use a constellation, which is a grouping of stars, which we can use as a position in the sky. We can say the sun is towards a particular constellation. So if we went out in March, and this is historic, so we can look at 1999's data here, we can go out in March and we can see the sun is towards the direction of the constellation Pisces. Go out in June, and now the sun is towards the constellation of Gemini, so we can see how many constellations this has moved around. Taurus and Aries were skipped. September, it's now towards Virgo, and Sagittarius in December. Now, if you look at what's going on here, the sun is at the center of the solar system and is standing still relative to us. And it's the Earth that's rotating around the sun. It's going around the sun in its orbit, and we're viewing the sun from different angles, from different positions. This is why the sun appears in different parts of the sky. And because of that 23.5-degree obliquity of the ecliptic, that means the sun in the summer, at least in the northern hemisphere here, reaches a higher altitude than it does in the winter. Now, the altitude of the sun in the sky is referred to by a specific name. And if we look at our ecliptic once again, here's our celestial sphere, north-south celestial poles, and our celestial equator. If we look at the ecliptic, the path of the sun across the sky, the sun will be at a maximum height compared to where we are at summer solstice, and a minimum height in the sky in winter solstice. And this is why we end up with different seasons. So the solstices are the points in a year when the Earth's axial tilt towards the sun is at its maximum. A summer solstice means that the hemisphere you're in is oriented towards the sun. In the winter, the hemisphere you're in is pointed away from the sun. Now, it should be noted here that the solstices are flipped from hemisphere to hemisphere. When it's summer in the north, it's going to be winter in the south hemisphere. And likewise, when it's summer in the south, winter in the northern hemisphere. So things are always opposite from hemisphere to hemisphere. If I'm talking about the solstices, I'll generally try to talk about them from the northern hemisphere, which is where we're experiencing from. So we've defined the maximum height of the sun in the sky and a minimum height in the sun in the sky. That's winter and summer solstice. So these solstices have an actual physical importance. They're not just to have festivals where hippies can go and get high. So we have our winter and summer solstices, and then we have our equator. We then have the ecliptic. The ecliptic, as you can see, actually crosses the equator. These two circles actually come together here and here. They intercept at 2 points. Those points, it turns out, are quite useful. The autumnal equinox is over here, and this is where we actually switch from the summer to the winter. This is when the autumn or fall occurs. The vernal equinox is over here, and this is where the spring occurs, when we're switching into the summer solstice. Now, these 2 points are extremely useful. Something we did in our previous lecture was we looked at the north point on the cardinal points on the compass, and then measured our angle around, and then measured altitude to a star. There was a significant disadvantage with that coordinate system, and that was that altitude and azimuth were not the same all over the globe. They were very much fixed to the horizon of the observer. So altitude and azimuth of a star will not be the same for everybody on the planet. Also, those coordinates changed a lot with time. Now, a coordinate system would be useful if we could set one up where it would be universal for everybody on the surface of the Earth. And that's where this vernal equinox comes in. This represents a point that is stationary relative to the Earth. So this point where the two circles intercept, we can call 0. And this will be the same for everybody on the planet. So our system of right ascension and declination can be used to measure the positions in the sky. Right ascension, given as the symbol alpha, or RA, is the angle measured eastward from the vernal equinox. The declination, which is analogous to our altitude, or this little delta here, or dec as it's written, is the angle measured north or south from the vernal equinox, so up or down. Now there is a little bit of an oddity to right ascension. Right ascension, or RA, is the angle measured east from the vernal equinox, as we said, but it's measured in hours, minutes, and seconds. It's still an angle, but rather than being broken up into 360 degrees, it's broken up into 24 hours. This is useful that even though we're quoting a position in terms of hours, minutes, and seconds, that position relates very well to the hours, minutes, and seconds that we divide our time up into. So that means we have a coordinate system that can also double as a system of measuring the positions of objects with time. So we know how they vary with time, and we know where they are. The declination, on the other hand, is measured in traditional degrees, from 0 at the equator to 90 degrees at the North Pole and negative 90 at the South Pole. Now, moving back to our discussion of the seasons, we have determined that the sun changes position in the sky and that its maximum altitude in different seasons alters. As the Earth's rotational axis is not 90 degrees to its orbit about the sun, so the ecliptic is not right on top of the equator, that means for half of the year, the northern hemisphere points towards the sun. For the other half of the year, the southern hemisphere tilts preferentially towards the sun. So remember, this was our obliquity of the ecliptic that we were talking about at 23.5 degrees. So over the period of a year, we can see that different hemispheres point towards the sun. So here's the axial tilt of the Earth compared towards the sun. So it's not spinning this way, it's spinning this way. And that's that obliquity we were talking about. So in December here, the southern hemisphere, here's Australia, is pointed towards the sun. In June, the northern hemisphere is preferentially pointed towards the sun. Now, there's a common misconception that the change in the seasons, the fact that it's colder in winter than it is in summer, is due to the distance of the Earth from the sun. This is not true. The Earth's orbit is quite circular, and we stay roughly the same distance. I say quite circular, it's not quite. It is a little bit elliptical, and technically, when it's summer in the northern hemisphere, we're actually a little bit further from the sun. But because we're oriented towards it, pointed towards the sun, we get more energy. So on the equinoxes, this is the time when the sun is on the equator. When the sun is on the equator, we're pretty much uniformly illuminated. So these yellow lines are the light coming from the sun illuminating the Earth. So in the northern spring and fall and the southern fall and spring, everywhere on the globe is pretty much getting the same amounts of energy. The sun is on the equator when it's on the equinox, when it's at a point where the ecliptic and the equator are intercepting. And these occur on March 21st September 23rd. During the winter solstice in December 22nd, now you can see that the southern hemisphere is pointed towards the sun. So this would be the northern winter solstice. So at this point, the sun would be the lowest point in the sky for the people in the north. Here's our equator, here's the sun illuminating the earth. And June 21st, for the northern summer solstice, you can see we're pointed towards the sun. So why does that make a difference if we don't actually change our distance from the sun? The reason being that the amount of light we receive at any location changes over the year. So here's our familiar, in most places other than the equator, cycle of winter, spring, summer and fall. Also, it's important to remember the sun's energy output does not change. The sun, well, it does a little bit, but for our purposes, it stays about the same. So the sun is pumping out energy at a rate of about 1,000 watts per square meter. So a square meter of area on the sun gives out about 1,000 watts of energy. And the Earth is always intercepting the same amount of radiation from the sun. The Earth's tilt, of course, is why we get less energy in winter than we do in summer. And that's because the energy is spread out over a larger area in winter than summer, because we're tilted away from the sun. And what I mean by that is, if we're looking here and we're looking at the energy from the sun just beaming straight down onto a patch of ground. So here's that 1 kilowatt per square meter coming from the sun, beaming onto the floor, beaming onto a square meter. Now, the winter sun is lower in the sky. That means the energy, the rays, are coming in at a much steeper angle here. That means that we end up, or shallower angle I should say, and that means we end up with the same amount of energy spread over 2 square meters. So the same amount of energy is spread over twice the area. This means the amount of energy the planet receives per square meter is actually reduced. So while the same amount of energy is coming in, it's spread over a bigger area. And that is why it's colder in winter than summer. So take note of that. The reason we have the seasons is to do with our axial tilt, not our distance from the sun.